Hello and welcome back. If you follow the channel, you know that we rescued two MMD-1 Mini Micro Designers, an 8-bit microcomputer trainer based on the Intel 8080 chip introduced in 1976. Over the previous episodes, we restored both of them to working condition. After we played with them in glorious machine code assembly for a bit, we started our quest to run Microsoft Basic on this minimalist machine. We started by adding 32K of non-volatile FRAM memory in the previous episode. After a bit of a fumble, we got our modern wonder of a memory going, and yes, the bits stay in there even after you turn off the device. But that's not enough yet to get up to par with the Altair big boys. To load and run the original Altair Basic, we need a teletype terminal, and for that, a serial connection, which you added to the Altair with one of these large serial I/O cards. This one is called the 2SIO with 2 ports on it. Let's see, it has to fit in the space left on the side of our breadboard, since we already consumed a big bit with our FRAM module and the 74LS00 gate we added to patch up our poor design decisions. So some shrinkage is probably in order. But not with modern wizardry this time. We are going to use genuine vintage chips that would have been available in the 1970s. In fact, the exact same chips that I use in the Altair 2SIO card. The shrinkage will have to come from our own clever digital designs. But thanks to the MMD-1, we are getting better at it by the minute. Okay, now that we have an MMD-1 that has lots of memory and permanent memory at that, I would like to give it some I/O capabilities and not any I/O. I want to have something that imitates what the Altair does, so I can run Altair programs on my MMD-1. So for that, I'm trying to imitate the serial card that I fought with on the Altair. And because it fought me so hard, I know it pretty well now. So I have reused the same UART chip, the 6850 from Motorola. That was a part of their 6800 series chips to go with their microprocessor. On the Altair, it's a really complicated card with tons of chips. Oh my, the Altair boys went all out with their design. It's going to require some major simplification if we want to fit all of that on what space we have remaining on our breadboard. Fortunately, this is built around a second generation UART, or a Universal Asynchronous Receive and Transmit chip, the Motorola 6850. They actually don't even call it a UART. Motorola's hyperactive marketing invented a new name, the ACIA, for Asynchronous Communication Interface Adapter. Obviously, it didn't stick, it's a UART. What makes it second gen is that it implements control registers inside a chip that can be queried by the computer. Controlling the previous UARTs was done by independent control lines, like the ones telling you when a character has been received, and others for setting parity and character length. It's a blessing and a curse. There is something neat about the straightforward first-gen UARTs that you can set up with dip switches and also watch the status signals with LEDs. Just one pin for one function. It's like the good old delightful HP instruments with a dedicated, well laid out and precise button for everything, instead of the new ones with one mushy button tossed over to the side that supposedly does everything via menus, so you're just never sure what the cursed mushy button will do. Anyhow, enough ranting. In our case, it should be a blessing. It cuts down on signals to wire up and the associated glue logic. And it looks like the Altair people didn't get the message, mostly because they went for the most capable and universal design they could. But in keeping with the more integrated chip, we should just hand over our simplified hardware design to the firmware people and tell them to have a go at it. After they read the 100 pages of indecipherable data sheets, that is. We'll shed a tear for them, but that will help preserve our space on our breadboard. Now, how to simplify this complicated 2SIO card? First off, we only need one port, so one of the UARTs can go. Somehow the S100 data bus in the Altair also is demultiplexed with separate in and out data lines, so they have to be remultiplexed by these 3 state buffers and overcomplicated control logic. We, on the other hand, have an unmolested 8080 system with bidirectional data lines, so we don't need any of that. Good riddance. I'm not sure what they were smoking either with their flip-flop power-ready whatever circuitry, which appears to be the Altair mostly talking back to itself. So I'll happily cross that one out too. Our 8080 does not need to have a conversation with itself just to start working. The address decoding for the chip select in the upper left-hand corner requires more thinking. In the Altair it's made universal, so you can hardwire the serial ports to any I/O address that's a multiple of 4. So most address and anti-address bits are available for you to jumper to a giant AND gate, so you can select your favorite start address. We'll need some form of address decoding, but as you'll see, we'll be able to reduce that logic to basically nothing. Alright, things are clearing up. However, the blue line on the top is the one we can't ignore. It is wiring the first bit of address straight to the register select pin. It's a trick to switch between accessing the UART normal character in, character out registers and the fancy control mode registers via simple addressing. If you execute I/O instructions at the odd addresses, usually the standard address 21, you send and receive characters from the UART as usual. But if you use the even base address 20, you access the control registers instead. We want to preserve this so the Altair software is compatible with our serial I/O port implementation. Fortunately, the best feature of that trick is that it does not need any glue logic at all. Perfect for us. Alright, enough cleaning up already. We'll worry about the rest of the circuit in a minute. Let's try to wire up our UART in a simplified way in keeping with the clean and efficient design of our MMD-1. So here is our glorious Motorola UART, which we need to connect to the address bus, the data bus, and the in and out signals that we have on our breadboard. If you watched the previous episode, the in and out are the same as the memory read and memory write signals, but get triggered during an I/O cycle instead of a memory cycle. The data bus connections are dead simple now that we are using the native bidirectional bus. We just tie the two together. We'll see in a minute how to control the bus direction. The address bus is more interesting. First of all, this is I/O addresses, which only go up to 255 in the 8080 processor, so we are only concerned about the lower 8 bits. In our quest to avoid extra glue logic, we are going to tie A4 directly to the positive chip select 0 and A3 to the negative chip select 2. This will select the chip only if we have the shown bit pattern, which includes the addresses 20 and 21. These are the serial port addresses normally used in Altair software. Of course, it will respond to plenty of other port addresses too, but since we have nothing else there on our MMD-1, it doesn't matter. A0 is directly tied to register select to implement the same trick as on the Altair. And that's it for addressing. From a software point of view, our port will look like a genuine Altair serial port. We then combine the in and out signal via an AND gate, which we use as a NOT OR gate as we demonstrated in the last episode, and tie the output to the remaining positive chip select. This way the chip can only be selected during an I/O cycle and will completely ignore memory cycles as it should. We also use the same output signal for the latching input, so data is latched in and out of the UART at the right time during the processor in or out pulse. Finally, we control the data bus direction by tying the out pulse to the read not write pin. That will sync up the UART data bus direction with that of the processor. That's it for the processor interface, but we have a few more things to do. First, we need to tie the CTS and DTS lines to ground, or it will prevent the UART from working. Guess how I found out on the Altair. With that done, we should get serial data in and out of the chip. We'll use a SparkFun RS-232 level adapter to generate the correct plus-minus 12 volt swing signals and connect that to our favorite terminal. We should be all good to go except for one thing. The MC6850 does not include its own baud rate generator, the clock used to time the serial data speed. This should be provided by an external circuit at 16 times the desired baud rate. Ah yes, I had skipped over that in the Altair schematics. First off, let me cross out the various level adapters on the right. We replace that with our SparkFun module, which leaves us with the baud rate generator. It uses two chips, a Fairchild 34702 and an unusual 93L34 that the previous user already identified as an equivalent to the later standard 74259 TTL chip. This combo generates a boatload of baud rates that you can jumper to either of the two ports. I had trouble finding the 34702 until I realized it's more commonly known as the HD4702, a baud rate generator chip from Harris Semiconductors. The circuit used in the Altair is actually straight from figure 2 in the datasheet, but I was relieved to find another much simpler circuit in figure 1. Unlike the more complicated circuit, it cannot generate all the rates at the same time and tops out at 2400 bauds, but that's plenty fast enough for what we need. And this might fit on our breadboard. So we will use an HD4702 for our baud rate clock. It only needs a few components for the crystal oscillator, grounding a pin to indicate that we want to use, say, the internal oscillator, and grounding one of the other pins to select our baud rate. Perfect for our application. We are done with our MMD-1 serial port design. Now the big question is, will it fit on our breadboard? Only one way to find out. Let's plug in our Motorola UART, our baud rate generator, and our RS-232 converter. Okay, it fits, barely. Will I be able to squeeze in the additional oscillator components? The crystal, yep. The two caps, yep. Fortunately, they are small values. And yes, we can even squeeze in the resistor at the bottom. Phew, we can shoehorn everything. So let's wire this up. I'll put the labels of the pins we need to connect to help out. I like to start with the ground wires, then the power wires. Thanks to the judicious placement of my oscillator components, I only need one baud selection wire to complete the baud rate generator. We'll just move that wire by hand to select our speed. It's a bit lame, but it will have to do. Then we connect the output of the generator to the two clock inputs of the UART. Okay, that was much easier than I anticipated. On to the rest of the UART now. While we are in that area of the chip, let's wire the TX and RX lines to our RS-232 adapter. The wires go under the SparkFun board, which is plugged last in the actual build. Next, let's do the address wires. A4 to CS0, A3 to not CS2, and A0 to register select to replicate the Altair trick. Already done with the address bus. Next is the in and out signals, for which we need an AND gate. Wouldn't you know it, we have one left over from our previous memory glue logic mishap in the upper corner of our 7400. How convenient! So we wire out and in to the two inputs of the remaining gate. The output goes to latch enable and CS1 as we previously discussed. The out signal also continues to the read-write pin to regulate the bus direction. Well, we are already done with the control signals too. Now we just need to add our data bus lines one at a time, and they are conveniently laid out one next to each other. Done! I was a bit apprehensive of this breadboarding, but it wasn't half as bad as I thought. Thanks Ben Eater for this inspiration. All we have to do is to test it and toss our hardware over the partition wall to our software people. Oh wait, that would be me too. So this is what I have wired over here. And you can tell it fits in my breadboard. All the data wires. Here I have address A4, A3 and A0 wired to the pins we discussed. My little baud rate generator with its crystal, the two caps, the resistor, wired for 1200 bars. That's the yellow grounding wire. Let's see if this works. First of all, let me look at the output of my generator here. Do I see anything? Yeah. So, So we have a clock. It's very slow compared to the rest. So there it is. So this is my baud rate generator. I have 19.2 kilohertz, 16 times 1.2 kilohertz. So I have the correct bit rate. And that's about as far as we can test in the hardware engineering department. We need to involve the software team because the freaking chip doesn't even start until it's initialized by software. So here's what the software department people came up with. Since they are lazy, they copied mostly from what they did when they fought with the Altair serial card, with a few enhancements for the MMD-1. This is what it takes to send a test character repeatedly from our UART. First, we have to initialize the chip via the control register, or it won't even start. So the first instruction is loading the special reset code with the two rightmost bits set into the accumulator. We send it to the UART via an out instruction to address 020, which thanks to our trick address decoding will write it in the control register. That should unlock the chip for transmission. We rinse and repeat, this time loading the bit pattern for setting 8-bit characters, no parity, divide by 16 clock. It's a value we figured out by reading the always very clear instructions from the datasheet, which we write again to the chip control register at address 020. Finally, our chip should be initialized and we can try sending a character. But before we do that, we have to make sure we have finished sending the previous one so we don't start writing over it. Given the low baud rates, sending the previous one could indeed take a while. So this time we do an in instruction at 020, which will read the control register. By the way, the bit meanings when reading the control register are completely different from the ones when writing to it. Internally, these are two completely different registers presented to the same address. Here is our little MMD-1 enhancement. We display the control byte we received on the rightmost LEDs. The only thing we have to do is an out at address 02, and that will write what's currently in the accumulator to the LEDs. See, the Altair guys can't even do that with their dumb LEDs. Then we test the value of the second bit only using an AND with a binary mask. We need to wait for that bit to go to 1 before we can send something new. So we jump back and keep reading the status bit if we see it's still 0. Eventually the queue will free up, the status bit will return a 1, and we proceed to what we really wanted to do, send our single character. So we load the ASCII code for an A, which is 101 in octal. And finally, we can send our character to the UART. This time we use address 21, which thanks to our address trick will load it into the data register this time. The rest is automatic from there on. The UART takes the character and starts sending it immediately with the correct baud rate and parity. We should see it printing on our terminal. So we just loop back, wait until the UART is done to send it again. Whew, that was quite a bit of work to send our poor character. It better works now. So I've written this program at address 5000. So let's go to 5 high and let's go. And already I sort of see it's a good sign here because on my status byte I have the 1 that tells me it's received nothing, and I see the out that's faint. It's sending stuff and then resetting itself, so that's the bit it tests. We should see evidence of that on the scope. And there you go. So I'm triggering on the in pulses. So this is where I read the status before I send something. Most of the time I'm triggering at a place where the queue is full because I'm continuously sending stuff and sending is way slow. Let me check that I am getting my AND gate wired as an OR. I am. Right, in or out, it's coming out, so that's correct. I think I should see my bits coming out if I am out of here. Yeah, I see bits coming out. It's so slow. There you go. So I hope this is an A. I don't know for sure. We have to check that out. Let me see if I can catch a send. Trigger and edge burst on. Oh, I'm doing it. Here's a burst. Okay, that's one of the moments where it found the queue was empty. So this is my in, it reads the queue. This is my out, it puts it on the LEDs, and it's empty. So it's going to do a second out, and that's the one where I send my data. So the next step is to actually connect that to a computer. I can plug my RS-232 converter. Then I can get that in, and serial port, or new open, there we go. Oh, I have an H. What the heck? And it's me sending something, right? If I reset it, okay, it stops it. 005 high, and go. Oh, I have B. 005 high, 022 low. It's a B. I put the wrong number in here. Let's try 101. Step, go. Aha! And now I have A's. Okay, so it outputs correctly. Let me see now if it inputs correctly. I haven't tested that yet. All right, we are transmitting. Can we receive though? For testing that, we need another trip to the software department. This was our previous program with the initialization block, the wait block, and the send block. We'll keep all that, but we'll make some room in the middle by adjusting our addresses and our jumps so the loop still works. We add our new receive routines in the created space. Like before, we have a wait loop, except this time we wait for the UART to tell us that it has received a character. It's the same in instruction to read the control register, and the same out to display the status byte on the right LEDs. But this time we test the first bit instead of the second one. It's the bit that indicates if a new character has been received and is ready for us to read. We keep waiting until this bit turns on. At this point, we issue another in instruction, but this time at address 21, in order to read the UART's data register, which should contain the received character. We upset our Altair friends again by displaying the received character on our center LEDs. Then we also save the character to register B so we can reuse it in a few lines. We go straight through this leftover no-op, not sure what it was doing there, and continue into the unchanged send wait loop. The output queue should be clear though, and we should go on to the send routine. However, instead of loading a constant character, we now load our just received character from register B. That's the new move B to A instruction. We then send it back out using the previous code. At the end, we jump back to waiting for the next input, so every letter we type should be received, displayed on the LEDs, and echoed back to our terminal. It's the quintessential loopback test of a serial link. If that works, we're golden. Our homebrew serial port works. And go. And it's... I'm not sure what that means. It means it has nothing in the output queue and nothing in the input queue. So if I do character, yeah, it's padded back, and I'm not sure of the ASCII code for H, but I know capital A is 101, so A, 101, we got it. B, all right, C, D, E, F, G, H, K, L, M, N, Oh, P, you can see it's looping it back, so... Oh, how do I do line feed on... There you go. Subscribe to CuriousMarc channel. All right, we have serial communications. I got the right characters. It echoed everything I typed. Okay, so since now it looks like an Altair with lots of memory, we should be able to run Microsoft's basics on it. Well, we should. However, Mr. Gates must have known I was coming and made it way more challenging than I originally expected. But that's a story for another episode. See you then!